Hello, everyone. My name is Jeroen Domburg. I work at Espressive Singapore nowadays, and I do all kinds of stuff, amongst which is to give a presentation to you guys about the Bitscrambler. As it says on the slide, the Bitscrambler is a solution for out-of-order bits, and how that works exactly, I will dive into. So, first of all, a few caveats. This is about a peripheral for the ESP32 line of series that is not out yet. This is a tech preview. If the peripheral gets out, then it'll be in the ESP32 P4 initially. However, that's an if and not a when, because we haven't silicon tested yet. So for all we know, the Bitscrambler, if you turn it on, might just let out a magic smoke or something. We don't know. We're gonna figure that out. We can already tell you what it'll do if we get it to work. Also, a few things about the tooling here. I'm going to show you a few programs that are Bitscrambler programs. The exact details of that are also not entirely worked out yet. We think we have it more or less down, but that might also change. So this is effectively the disclaimer. So with that out of the way, what is the use case for a Bitscrambler? What practical problem does it solve? Well, the thing is that ESP32 chips always have had lots and lots of peripherals. So this is a block diagram of the ESP32 P4, and you can see that there's a lot of peripherals that are non-single use. So you can prod them in order to do other things than that they are actually made for if you really need to. With all that, you could probably control like 90% of all interface needs, sensors, other microcontrollers, other things. But that's only 90%, and we would like to improve that number at least a little bit. So what exactly am I talking about? You need to, what's in the 10% that we're trying to get? Well, for instance, this is a real-life example. A customer came to us with some sort of unknown chip. I think it even was internal. I'm going to say it's a camera. I don't exactly know. The trick was that the interface to it, the data that is sent to the ESP, was in a weird SPI-like format. So just like SPI, if you know SPI, it has a clock line that just goes up and down. That's the clock. And on that clock, every time the clock goes up, there's one bit being sent out, and that happens 8 times, and then 8 times, and then the ESP receives a byte. So that is not exactly how the camera works. The camera has 3 of those data lines: one for red, one for green, and one for blue data. And each single one of them sends out 1 bit per clock cycle. So it is not impossible to connect this to an ESP32. For instance, we have quad SPI, which is SPI using 4 data lines. It sends one nibble every clock, so 4 bit. This generally is done to make everything faster. You only need 2 clock pulses in order to send a byte and not 8. So this would kind of map to the current device. Namely, we could just connect the red line to D0, then the green to D1, and the blue to D2, and then we have a D3 left, which will just tie to ground or something. And the clock can go to the clock, and this is physically compatible, and also logically compatible, because we receive data on multiple lines every time the clock goes high. So the only issue is that if you do it like this, the way the data ends up in RAM is going to be all cattywampus, because the quad SPI is intended to receive nibbles at a time, and it receives 3 bits at a time. So if you now want to process this data, you first need to get all the reds together into 1 byte and all the greens into 1 byte, etc., which is a problem, at least for those people that was. Another example, something a little bit less obscure. So you know those SPI LCDs, right? They usually have the SPI ports, which consists of data, clock, and chip select. And they also have a DC line, which is a data or command line. The idea is that if you do an SPI transaction with that high, then you're sending a command, and if it's low, it's data, or the other way around, I don't remember. So it effectively looks like this. So if I send some sort of transaction with the DC line low, then it's data, and if it's high, it's interpreted as a command. So a command is, for instance, turn on the display. Well, data is, okay, this pixel needs to have RGB 1, 255, 1, something like that. So this is all very, very nice, and the ESP has absolutely no issue controlling this. However, some displays work in what's called a 9-bit mode, and the idea is that they get rid of that data/command line. Instead, what they do is, rather than sending bytes, they want you to send 9-bit values, and those are the same as the bytes, but the very first bit is the DC indicator. So if that is low, then it's data, and if it's high, it's a command. That's all nice and well, but that means that all of a sudden we need to send 9-bit values. Well, SPI doesn't care. SPI just reads data from memory and sends that out of the SPI port. However, it does mean that we now need to put 9-bit values into memory that is byte-wise oriented, so 8-bit in width. So you would get something like this if you were to look at the memory. You would get a pattern that's shifting. And again, it is possible to do this using an ESP, but it is it is not very nice to do. So as I said, it's possible. You simply reorder the bits. It's like trivial, right? And then you actually write it. So this is a little bit of code that reorders 3 bits in a byte. And then you figure out that it takes 6 instructions, one of them is a branch, in order to reorder a bit. And this is on a fast RISC CPU, but still 6 instructions per bit. That is a fair amount of time that you're just swapping around bits if you want to send, for instance, a picture to an LCD or something. So maybe we should do something about that. Maybe we should have some sort of accelerator, possibly. And this is exactly what the Bitscrambler is. The Bitscrambler is, as it says, a bit parallel, very large instruction word programmable state machine in the DMA path. So what do I mean by that? Well, let's start with the DMA path. The ESP32P4 has a bunch of peripherals that use DMA in order to fetch their data from memory and send the data back. It actually has more than the ones circled around, but these are the peripherals that you generally would want to use with the Bitscrambler. The DMA path works like this. If, for instance, an SPI device wants to send some data rather than ask a CPU to manually put that in, you give it a certain block of memory, and the DMA interface is responsible for fetching that data and sending it to the SPI device, which then sends it on to the actual device attached. If you want to read from an SPI device, the same idea, but the other way around, data gets sent from the SPI peripheral to memory. So now you can introduce a Bitscrambler in these paths. In this presentation in general, I'll be talking about the path from memory to a peripheral, like, for instance, the SPI peripheral. Everything also goes for the other way around. For if you want to send data from a peripheral to memory via the Bitscrambler, that's possible. And it's actually even possible to do memory-to-memory transfers via the Bitscrambler if you want to scramble your bits without having to send them to an actual device. So what does a Bitscrambler look like? Well, it kind of looks like this. It has an input, it has an output. These are the things that go from memory to the peripheral, or, as I said, from a peripheral to memory, or even from memory to memory. And there's a little, let's call it a CPU in that block. And that CPU runs a little program. And as an example program, just to give you an idea what it looks like, let's start here. So you first see the read 16 instruction, and as it says, it reads 16 bits from the incoming DMA data. It then uses a set command, and what the set command does is it routes one of those bits to an output bit. So in this case, in the output word, bit 0, you'll set that to whatever value the bit 0 on the input is. And obviously, this is fairly trivial because you just route the bit directly. But the idea is that you can use any values there. You can take all your bits on your input and scramble them to any bit on the output if you want to. So you can do that, and as I said, this is a little CPU. So at the end, if you want to write the data to a peripheral, you also need to actually do that. There's a fair amount of use cases where you don't want to do that, which I'll get into later. And finally, because this is a CPU-like thing, the entire thing is a loop, so you would like to jump back to the start of the program. So you've seen the example. What specific operations do you have? Well, there's only a few. They fit on one single slide. So you have the set, which, as I said, sets the value of an output bit to some input bits value. Read and write read data from the DMA stream, and write data from the DMA. Write data to the DMA stream. If you've got your jump, that jumps back to another place in the program. You've also got loop, which uses one of the counter registers, which I'll get into later, in order to loop over a bit of code multiple times. You've got add, that can add something to a counter. You've got if, that can jump to a certain location only if a certain bit is set. You've got these two commands, which load your counters either from a direct value or from some data read from DMA or somewhere else. And finally, no operation. You also have that. So these operations, you may have noticed that I haven't called them instructions, and that is because they are not. They actually go together in, I'm going to call them an operation bundle. So this is multiple of these things bundled together. You can have up to one read and up to one write. You have up to 32 sets, which means that you can have one set for every single bit in the output register. The output register is 32 bit. And you have one other, so a jump or a loop or one of those add or load control, load counter direct or load counter indirect operations. And this limit is so weird because one operation bundle actually is one instruction. The Bitscrambler is a pretty weird architecture that uses instructions that are not 32 bits or not 16 bit. No, instructions are 257 bits wide. We tried 256, but it was one too little, so 257 bits wide. So that's a very long instruction word, and on the flip side, unfortunately, the reason why these are all bundles is that you can execute one of those very large instructions every clock cycle. And given the fact that the DMA subsystem, I think, runs at 200 megahertz, that means that you can shift 32 bits, every single cycle of 200 megahertz. So this thing is very, very fast. So the downside of very long instruction words is that we don't have that much address space. We only have address space for 8 operation bundles for 8 instructions. But given the fact that these things are so powerful, it tends to be enough. Okay, on to the details. I've mentioned counters a few times. We have 2 counters here. They're called A and B. They're both 16-bit. So loop uses them in order to loop over a bit of code, and pseudocode is here. It effectively counts a certain amount. It adds a certain amount to a counter until it is equal or more than the final value. If it is, it falls through. If not, it jumps back in order to loop another time. Pretty standard. And then you have the load counter direct, which just puts a value directly into a counter, and you have the load counter indirect, which loads some sort of value that is read from DMA stream or somewhere else into the counter. Both these can have masks, so they can only set the high or the low value of this, and that can be useful if you want to have 4 8-bit pseudo counters, more or less. You also have add. You can also add a direct value to a counter. And set actually also makes use of the counters. You can have you can address a bit that is offset by a certain counter. So if say my counter A is 3 in this example, then my output value would be set to the input bit 4 in this particular case. And that allows you to iterate over the individual bits in a loop, and that can be useful. So readable registers, we already mentioned a few. They're used by set, they're used by if and if not. And specifically, they are 0 to 63. They're just called 0 to 63. They don't have a name aside from that. These are the bits that are read from DMA. You can access like the last 64 bits. 00 to 031 are the old bits, the ones that are sent to the output the previous cycle. So you can look back at them and use them in order to generate your output bits for the current cycle. That also means that you can recycle them. If you select a bit on your output, a bit on the O register for your output, that means that the next cycle that bit will appear on the O register again. You've got your counter registers, you can also read those, and you have your aux bits. And aux bits have a bunch of comparators in there that compares the A and the B register and the O register in certain ways. It also contains a fixed high and a fixed low bit. So if you want to send that, you also can. Finally, you have the LUT RAM, and there's a little lookup table RAM in the Bitscrambler. And what that is, I'll get into later, but just know that you can also select those outputs. So any of those registers, any of those bits, you can send to any bit on the output. That is important to know. Okay, so on to the details. As I said, 0 to 63 retains the last 64-bit read from incoming DMA. How that works is the incoming DMA is fed into a 64-bit FIFO, more or less, and the read command actually shifts down the data. So it pops out the oldest data and shifts in a certain amount of new data. So here's a little illustration. If my 64-bit incoming DMA register starts like this, 10, 20, etc., then if I do a read 8, which means read 8-bit, then the entire thing would be shifted up by 1 byte, and the new byte would drop in. So 90 here is pushed in. Same goes for if I do a read 16, but now 2 bytes are put in, and the entire thing is shifted up 16-bit. So the LUT RAM, LUT stands for lookup table. That is what it's used for. So you give it a certain address, and then it'll return the data that is at that address. And that is used for ALU operations. As you might have seen, we don't really have an ALU. You can't do AND or XOR or add or whatever. If you want to, you can use a lookup table in order to do that. You can also do more complicated operations. So for instance, data conversion. If I want to have a picture in linear space, and before I send it out, I want to convert it to have a gamma curve. What I could do is load the gamma curve in my lookup table RAM, and then use the Bitscrambler to automatically convert the linear data to one that has a gamma curve on my way to a display of some sort. So the LUT RAM is initialized on startup of the Bitscrambler, so you can just dump any data you want in there, and the Bitscrambler program can make use of it. And you can use it in 3 configurations. As you see, they all have the same amount of bits, but the ordering is a bit different. You can have 2K bytes, you can have 1K of 16-bit values, and you can have 512 32-bit values in there. This is also selectable on startup. And if you want to figure out how it works in C, it's kind of like this. It uses the most significant bits of the O register in order to look up a value. And LUT out is something that you can select from, so you can send bits from that to your output. Okay, that is more or less the Bitscrambler. And I can imagine that you guys are all dazed and confused. now, and it's probably a good idea to finish up with a few examples that will also give a little bit more of an idea what you can do with it. So in order to illustrate that, I don't want to just plunk assembly at you. So what I'm going to do is I have an illustration of the data path here. So you have the 5 registers that you can read from on the top. You can select any bit of those and move it to your output. So that is the green lines. And from the output, the red line, there's data going back to the O register where it's stored for 1 cycle. And you can also load the counters from there. Finally, the O and the A and B registers are compared in various ways in the CMP unit, and the O register also works as an input for the lookup table. So first example, we're going to swap bytes. So what you sometimes have is that you have a stream of 16-bit values incoming, but the endianness is wrong. So what you need to do is for each 16-bit value that comes in, you need to swap both bytes. So that's illustrated here. 0123 becomes 2301, etc. So this is peanuts for the Bitscrambler. It's a very simple program. Actually, only one instruction bundle. So first, we use the set instruction to set the lowest 8 bits of the output to bits 8 to 15 on the input. We do the same with the highest 8 bits, or actually bit 8 to 15 on the output. We set that to the lowest 8 bits on the input. Then we read 16 bits into the memory register for next time. We write the 16 bit we just assembled, and finally we loop back to the beginning of the program. So in the data path, it looks like this. The lowest 16-bit of the inputs are routed to the lowest 16-bit of the output register, but the bytes are swapped in the middle. So that's it. So we have another thing here. I think I'm missing a slide. I'll just explain. So if you have a display might be very big, like 800 times 600 or something. And the issue is you tend to need to have a frame buffer, which is enough memory to store the RGB value for every single pixel in that display in. So that means that if we go by a very fancy display that does 24-bit color, that means that you need to have 3 bytes for every single pixel. That might be a bit much. So there are tricks in order to minimize that. And one of the tricks is to not store 3 bytes, but to store 1 byte and have every 1 byte be mapped to a certain RGB value that is in a separate bit of memory there. So effectively, you have a palette of 256 colors that you can select out for each pixel, and what those 256 colors are in a different bit of memory. So you can use the Bitscrambler in order to do that as well. I'll start with the diagram. So what you would do is you would read your index, your 8-bit value, and you would route that to your output register. And you only do that so it ends up in the O register, because we're going to need that later. In the second instruction, the output from the O register is active, and that is by default sent into the lookup table. And the lookup table contains your RGB values, so it'll look up the RGB value that goes along with that. And you can then route that to the output register, and now you have the RGB that goes along with it. So what that looks like in code is this. Again, it's a very simple Bitscrambler program. In this case, it's only 2 instruction bundles. So the first bit is, as I said, we route the incoming byte to the topmost byte of the output, because that is where the LUT will be connected to. And we also read the next byte because we have to do that anyway. And then the second thing is we just select bits from the LUT, because the LUT already has done the conversion for us, and then we write it, and that's it. So a final example, this one is a bit more complicated, the 9-bit LCD. You might remember it. So we have 8 bits of data, and we need to prepend each bit of each byte of data with a data or command value. So the way I envision this is you have your bit stream with your values, and then you prepend that with 1 byte that indicates if this is going to be a data or a command. So the way this looks like in the diagram is like this. First, we process that initial byte. So we select that specific byte for the output register, and then we load that into register A, so we can use it later on. So after we've had that first bit, we start processing, and we do that like 32 bits of actually 28 bits at a time. So we read each byte from the input register, and we send it to the output register, but we intersperse it with a DC bit. And the issue is that the output register is only 32 bit, and we occupy 4 bits by the DC thing. So from the last byte that we read, we only can output 4 bits. So in the next cycle, we need to still output those last 4 bits, and then we can also output 3 more bytes, and then we're at an even number again. And if we do this every time, then each clock cycle we will output 7 bytes on the output. Every 2 clock cycles we will output 7 bytes from the input to the output. That's it. So the code for this is a bit more complicated, but it's mostly because of we need a lot of set commands to write the bits in the right order. So we start out by loading bit 0 into the A register and reading 8 more bits. And this is the first half of the actual sending bit. You can see the 4 bits are sent to A0, which contains our DC value. And this is the second half of the moves. At the end, we need to read another 8-bit because we read in a weird amount, so we have to split that in 2 reads, and then we jump back to the loop at the beginning. So I hope that made it all at least a little bit more clear. If not, then please look forward to the TRM as soon as we release that, and I'm sure that there will be a bunch of examples that will end up in ESP IDF as well. So as I said, we hope it comes out in ESP32P4, and this is the end of my presentation. My name was Jeroen Domburg, and this is where you can reach me. Thank you very much for listening.